All right, ladies and gentlemen, online world, you are now with us. Welcome back to your favorite class. Announcements. Your lab report is due if you're in the Thursday lab. We'll be due at the beginning of your lab period tomorrow. So make sure you get that in, the final draft of your combined loading lab. Those of you that turned it in yesterday, I tried to turn them around in 24 hours, but I got sleepy last night. Sorry. Okay. I think I got most of them done. I think there's 2 people that have not yet received feedback from me. So I try to stick to my time. Okay, sorry. Okay. So turn that in. Also, homework number 3 is posted. That'll be due next Monday. Only 2 problems. This is on 3D stress at a point. So do that. You got some MATLAB there. So brush off those 190 skills. All right. And make some nice looking functions. Darn it. Okay. Let's talk about where we left off. We were in the middle of an example problem. So I'll bring up that example problem and then kind of bring up where we left off. Remind you, this was our example problem here. So we had a full 3-dimensional stress state at some point in a body, and we were asked about what is the normal stress on a plane if we were sort of realign our axes into a certain orientation. So a normal axis sits at 61.3 degrees with respect to x, 53.1 degrees with respect to y, 50.2 degrees with respect to z. We are asked to calculate the normal stress on the oblique surface that would be created with that particular cut. And then we are also asked to determine the principal stresses and maximum shearing stress at the point. So this is our example. I'll kind of bring up the writing pad where we had left off last time. So that was kind of here. This was our particular problem. Get rid of this quickly. Here we were. So we kind of wrote down the given information, our stress in x, y, and z, and our shear stresses x, y, x, z, and y, z. And we were also given these angles with respect to the normal. We were asked to find the normal stress, and principal stresses 1, 2, 3, and tau max. So we had kind of worked our way through the normal stress on this oblique cut surface by using our stress transformation equations in 3D. That's this sort of equation here, where these directional cosines were assigned based on the angle of the normal with the XYZ coordinate system. After punching everything in, we found that that normal stress would be 12.3 KSI. So to finish off the problem, we need to do the principal stresses. And so for principal stress, this is just kind of plug and chug. We derive the equations that are used for calculating the principal stresses. And this was that cubic equation that had those invariants in it that we'll use to solve for the principal stresses. All right. So the equation for principal stress is this cubic equation, which is sigma cubed minus I1 sigma squared plus I2 sigma minus I3 equals 0. Where remember these terms here, I1, I2, and I3, these are called the stress invariants. Right. So we'll remind you what those are. I1 is just sigma x plus sigma y plus sigma z. By the way, your equation sheet doesn't use I1, I2, I3. It uses capital A, capital B, capital C. Whoever wrote that equation sheet, I don't know what they were doing because I've never seen that before, but you know, wasn't me. All right. You can punch these in here, sigma x, sigma y, sigma z. It's 10 plus 12 plus 14. I'm not going to write it all down here, but here we'll get 36 KSI. Invariant number 2, as a reminder, sigma x times sigma y plus sigma x times sigma z plus sigma y times sigma z minus the shear stresses squared, tau xy squared minus tau xz squared minus tau yz squared. Again, I'm not going to put all the numbers in here. I believe that you can punch those into your calculator, though, you know, watch your numbers, I guess, if you are punching it in. And notice here that the units are going to be KSI squared. So here we're going to have 228 KSI squared. So that's invariant number 2. Invariant 3. Here we have sigma x, sigma y, sigma z, minus sigma x, tau y, z squared, minus sigma y, tau x, z squared, minus sigma z, tau y squared, plus 2 tau xy, tau xz, tau yz. Right. Punch all this in on your calculator. You will have a negative 1,752 KSI cubed. All right. So those are your 3 stress invariant values. Those get fed into the coefficients of the cubic equation that we can use to solve for principal stresses. So then we have the following equation to solve for the principal stresses. Going to be sigma cubed minus 36 sigma squared. Okay, that comes from I1. We have here plus I2, so this is going to be plus 228 sigma, minus I3, but I3 is already a negative, so we have a plus 1752 equals 0. This is the cubic equation in sigma that will help you solve for the 3 principal stresses. All right, cubic equation, 3 answers. So here we go. Solve this using whatever solver you want. I think most calculators have like a cubic solver nowadays. Is that true? Most calculators? Maybe. Otherwise, you can graph it and see where the graph intersects with 0. You know, that's also fine. And so your principal stress is sigma 1, 2, and 3, ordered from greatest to least. That's just generally by convention. It's going to be 22.1. And negative 4.3 KSI. All right, so that would be your answer for this problem, solving that cubic equation. All right, to cap it all off, we have to solve for the maximum shear stress. And we said that if we order our principal stresses from greatest to least, then the maximum shear stress is going to be the first minus the second principal stress divided by 2. Now, tau max, which here is sigma 1 minus sigma 3 on 2. And again, this is under the assumption that sigma 1 is the greatest and sigma 3 is the least. So here this is 22.1 plus 4.3 all on 2. Or our max shear stress here is 13.2 KSI. You might have to work some tricks in MATLAB to order your stresses properly so that you're always getting the max shear stress when you write your function for homework number 2. Yes. All right. Questions on this problem from audience or virtual audience? So it's funny, my fiance now, she watches like her church every Sunday. Joe claps for me, thank you. I found someone that can put up with me for more than 5 minutes. Okay. She watches her church online every Sunday, and I call it churchual. That's kind of funny. Okay. She laughs when I say that. Okay. Questions? No, they just say congrats. All right. Well, thank you. So Jordan, I'm off the market. Sorry. Okay. So no questions on this. That concludes the 3D stress at a point notes, and we'll move on now to the next set of notes, which is failure criteria. And I've uploaded a new slide deck to Blackboard, so take a look at that and get those notes if you haven't done that. So, new stuff. Yes. got like an indication that I got stuff going on, but I think that's just people popping in the chat. Yeah. All right, so new set of notes. And that's failure criteria. So, we really have to hammer in and hammer home on principal stresses before we talk about failure criteria, because failure criteria for materials are dependent on your ability to calculate principal stresses. Pretty much every failure criteria that you see for materials will use principal stresses as a basis. So we have to sort of be very comfortable and familiar with principal stress to do that. So here we go with static failure criteria. Yeah, she's no longer my girlfriend. She's my ex-girlfriend. Okay, static failure criteria. And I want to sort of motivate this with an example of how you might go about like determining the failure of a material. All right, so let's think about how you might do this in a lab. All right, I give you some bar of material and I ask you what's the yield stress. What are you going to do? You guys took material science, right? Did you take material science yet or not? Haven't had material science yet?
We're in the process.
Oh, okay. Well, I give you a bar of aluminum. You go to the lab and you pull on it until it starts to, basically fail, and you can sort of see that visually. And so you basically will calculate, all right, what's the force that thing failed? Divide that by the cross-sectional area of a piece, and that's like the failure stress. Okay? And that's pretty easy to do if you just have one direction of loading on that bar. Okay, but what if you have multiple directions of loading, which is all kind of contributing to a stress state at certain points and complicated? Okay, so if you just have like one-dimensional stress, yeah, failure is easy. You just divide the failure stress that you see in the lab by the cross-sectional area, and that's your failure stress. All right, but if you have multiple loads on your thing, it's a lot more difficult to say, all right, if you got this much shear stress, this much normal stress, this much whatever, is it going to fail or not? Well, I don't know. I know the yield stress of this piece, but I don't know if that stress state is going to cause failure. So we have to have some criteria to deal with that. So let's think about like a simple experiment that might help us on our way. And that is just like a cylindrical rod in tension. And we're going to pull on it until it starts yielding. All right. So here's our rod, our cylindrical piece. Okay. We're going to apply some stress to this. Right. Let's say we'll just call it, we're going to apply some load, some tension. T for tension. T for terrific. All right. And we'll load until failure. I can hear them like doing that pounding outside. You guys hear that? Yeah. Anybody live like within, a couple blocks of that? It's got to be annoying. I hear they start at like 7 in the morning every morning. Don't you need to set your alarm? So load until failure. And let's say that like it's just about to fail. It's really close to failing. And we'll say that the failure stress, or what we call the yield stress, is going to be given by sigma sub 0, sigma naught. And this is like the tension at failure divided by the cross-sectional area of this particular piece. All right, pretty straightforward. It's like a one-dimensional type loading scenario that we have going on. Right? If we look at an element at some particular point, we can do this now. We're pros. We got some element there that we're going to blow up. You could even do it in 3D if you like. Right? So right at failure, you more or less have this particular state. Okay? No shear stress, No stress in like what would be the x direction. You just have like this sort of condition. If you do just your standard x, y coordinate system, stress state is no shear stress, nothing in x. The only thing in y is the stress that gives failure, and nothing in z. This is your full stress state, three-dimensional stress state at the point where this thing is just right about to fail. Okay? If this is your stress state, you could punch these values in to that principal stress equation that we would have, and you would see pretty quickly that the principal stresses would be the following. Maybe some of you online are hearing that banging right now. Wakes me up every morning, says Michael. Yeah, it's like Chinese water torture on my ears. Yeah, okay. Sorry, Kurchma. Buy some earplugs. I don't know. All right. We remember we had that sort of principal stress equation. You would get the following principal stresses. If you plugged those stress values into that principal stress equation, you would have sigma naught, 0, 0. Those would be your principal stresses. Right? Now, what's the point? Okay. Well, the point is we've applied some force and we can sort of assign that particular stress value as like the failure value. Okay. And now it's up to us to decide, okay, this is a principal stress state which would cause failure. So we look at this right here and we say, okay, it's easy to see that with these principal stresses, we fail. All right. Now, can we set up some criteria so that if we have some other arrangement of principal stresses, some other arrangement of stresses, can we compare this known state of failure to the state that we currently have to see if it's greater than this or less than this? That's the general idea behind failure criteria. We know with a very simple one-dimensional experiment, it will fail with this loading. So let's compare the complicated loading situation to this situation through principal stresses to see if it's going to fail or not. Clear? Okay. So to see, we compare principal stresses of more complicated stress states to this known failure state. Okay, and we can do this in a variety of ways. The methods that we're going to talk about in this class, we have 3 different ways to compare. Okay, so the 3 different criteria that we're going to use. That we're going to talk about is what we'll say is the max normal stress theory. Okay. Max shear stress theory. Also sometimes called the Tresca criteria. Tresca. And the maximum distortion energy theory. also sometimes called the von Mises theory. All three of these theories have the same basic idea, all right? And that same basic idea is, let's look at some condition of the current stress state that uses the principal stresses, all right? So let's say I have some complicated stress state and I calculate my principal stresses at that point. Great. Now I want to compare the principal stresses that I calculate at that point to some failure criteria that I define using these sorts of theories. If it's greater than that, it's going to fail. If it's less than that, it's safe. It's the general idea. All right. So let's start with what is the maximum normal theory. All right. Let's say we have some complicated stress state. With all of the following things. You know, it might have sigma x, sigma y, sigma z, tau xy, tau xz, tau yz, right? Stress at a point can have all 6 of these possible values. Now let's say that we have done our analysis with these 6 values to get principal stresses. We just talked about how to do that, okay? So we do analysis and we get sigma 1, 2, and 3 equal to sigma 1, sigma 2, sigma 3, right? The maximum normal stress criteria says that if any of these 3 principal stresses exceed the yield stress of the material, you fail. Okay. If the magnitude of any principal stress exceeds the yield stress for that material, you fail. So you have this crazy complicated stress state. You calculate what the principal stresses are. If any one of those principal stresses is greater in magnitude than the yield stress, you fail. I don't like words. I like math. I speak math. So this is the actual criteria in math speak. If the maximum of your 3 principal stresses, sigma 1, sigma 2, sigma 3, is greater than or equal to the yield stress, you fail. Or if the minimum of any of these is less than or equal to the negative yield stress, you fail. Remember, we could have failure in both tension, which would be like that first condition, or compression, which would be that second condition. So let's look at what the failure envelope looks like for this. So let's investigate failure envelope. So what we're going to do here is we're going to plot sigma 1, sigma 2, sigma 3 in 3D space. Right? So here we go. And let's say I go through some analysis, okay, on some point that has a complicated stress state. That analysis is going to give me a sigma 1, sigma 2, sigma 3 that exists somewhere in space on this three-dimensional figure, okay? So let's say I do analysis and I got a point here that exists for one particular complicated stress state that I have. Or one stress state of interest. All right. I want to kind of create for myself a three-dimensional representation of the failure envelope for our particular failure criteria. What do I mean by that? Well, I know that if any one of these principal stresses exceeds the yield stress, I will fail. So what I mean by that is, let's go ahead and put on these individual axes the value of sigma 0. Maybe the sigma 0 is way out here for sigma 1, same for sigma 3, same for sigma 2. Okay. I know that if any of those principal stress values for my current condition, sigma 1, sigma 2, or sigma 3, exceeds that sigma naught, I'm going to fail. So I can sort of confine myself or make this sort of three-dimensional object inside of this three-dimensional plane that represents what would be a safe condition or what would be a failing condition, okay? So what I mean by that is, if this sigma 1 ever exceeds sigma 0, I will fail. So I can sort of make myself a line on this particular three-dimensional space here that says if sigma 1 ever goes beyond this line, I fail, right? Regardless of what's happening with sigma 2 and sigma 3, okay? Same idea with sigma 3. I can create this line here. Same idea with sigma 2. I create some line up here, okay? That says if sigma 2 ever exceeds sigma 0, I will fail. If sigma 3 ever exceeds sigma 0, I will fail. So what you end up with is sort of this series of lines that allow you to construct an object in this three-dimensional space that says if you have a stress state that gives you principal stresses, and that stress state results in a point that exists inside of this object that we're going to create, you're safe. And that object actually looks like a cube in this situation. I'll do my best to sort of like draw it. Hard to sort of draw this. Probably best if I, because it's actually yeah, this is hard to draw. Right. It's probably best. Okay, so this cubic space. There might be a better picture of it if I can. Nah, no good three-dimensional pictures. Yeah, that's too bad. Oh well. So usually, we look at failure envelopes in 2D by assuming sigma 3 equals 0. In 2D, failure envelope looks something like this. Again, we're plotting in 2D with principal stresses sigma 1 and sigma 2. And we're going to indicate in this two-dimensional space, hopefully it's a little bit more clear this way. And the idea is if your stress state exceeds any one of those lines, you fail. So if sigma 2 is greater than sigma 0, you fail. If sigma 1 is greater than sigma 0, you fail. If sigma 2 is less than negative sigma 0, you fail. And if sigma 1 is less than negative sigma 0, you fail. This is the general idea of this particular failure criteria. So that leaves us with a safe space that looks like this square here. So maybe you do your analysis, and your analysis tells you that your sigma 1, sigma 2 value lies here. Okay? Then you're safe. All right. Maybe your analysis tells you that sigma 1, sigma 2 lies there. Okay, well then you failed. You're outside the envelope. All right. So that's the max normal stress theory. All right. Let's continue with the next theory, and that is max shear stress theory. Now, assume we have a stress state again. With all these stress components. We can do the analysis here to get principal stresses again. Using that cubic equation. And one more further step now for max shear stress. Okay. This is something you could calculate for any arbitrary point given this known condition. All right, you could calculate your maximum shear stress. The max shear stress failure criteria says that if tau max is greater than or equal to sigma 0 on 2, you fail. And that is generally the condition. There's kind of two values here, but this is generally the condition. So it's more or less. Assuming that to be true. All right, if we want to look at the failure envelope here. So for 2D straightest stress with sigma 3 assumed 0. So your out of plane stress is 0. All right, here we are again with our sort of boundaries. And we'll say that if we assume, then this is one of our equations. This is one equation that gives sort of the boundary of our failure envelope. Right? So sigma 1 minus sigma 2 greater than or equal to sigma 0, that would be a condition for failure. Right? Could sort of rearrange this if you would like as, you know, sort of slope intercept form. This is what it would look like. Here, this is one line in our failure envelope that sort of defines one of the lines of the boundaries. Okay. So this line is simply this line here. My intercept is negative sigma 0. And it's sort of a slope equal to 1, sloping upwards. So this is a line that would define one edge of the failure. So this is failure would be down here. All right. How do I want to describe the rest of this envelope? Okay. If we do not enforce sigma 1 greater than sigma 2 greater than sigma 3, can look at other lines on envelope. Okay. If we don't enforce this to be true, then we could have something like sigma 1 minus sigma 2, sorry, minus 3 on 2 greater than or equal to sigma 0 on 2 is one of our lines. But if we assume sigma 3 equals 0 from, a state of two-dimensional stress, then sigma 1 on sigma 2 greater than or equal to sigma 0 on sigma 2 is one of our lines. Right? This would simplify to sigma 1 greater than or equal to sigma 0 causes failure. That would be this sort of line here. Another line on our chart. Showing that this would indicate failure. All right. There are a few other lines that we could make that would sort of follow this same trend, where you would assume like sigma 3 is 0. Those lines would look a lot like the max normal stress theory as well. Like here, and here, and here. But we have this additional sort of wonky one that comes from the max shear stress theory, where we don't assume sigma 3 is 0. And that would give you this line, and as well as this line. More detail about this in the notes. So the failure envelope here, if you want to stay safe, is this envelope here. All right. That's the safe space. I know I didn't do a great job explaining that. Apologies. It's better in the notes. Okay, but in general, the criteria is this. With sigma 1 greater than sigma 2 greater than sigma 3, if sigma 1 minus sigma 3 on 2 greater than or equal to sigma naught on 2, you fail. That's really all you have to know. This is the max shear stress criteria. Or sometimes called the Tresca criteria. Okay, that'll be it for today. We'll finish up with the maximum distortion energy theory on Friday, and then we'll do an example. Yes. Don't even need to set your alarm. That thing wakes you up every morning.